Gamma rays are the highest energy component of the electromagnetic spectrum. They are the highest frequencies, and these are the highest energies we receive as electromagnetic radiation from celestial objects. Okay, so today we will have a glimpse at the gamma ray universe, and we'll also look at telescopes which you use at X-rays and gamma ray wavelengths. Now, just to recap from what we said last time and earlier classes as well, that this is what we are focusing on today, gamma rays, and we'll also look at the kind of telescopes that one uses at gamma rays and X-ray wavelengths. And the reason why they are different from, say, optical telescopes is something we will try to understand. And then we will move on from that. Now, again, just to revise or recap again what we discussed earlier, that if I were to look at X-rays and gamma rays, the highest part of the electromagnetic spectrum, the most energetic ones, that if I look at gamma rays, that the wavelengths are less than about 10 to the power of minus 9 centimeters. And that is what you can see in this figure given over here. So these are not sharp boundaries, as I mentioned earlier, but these are easy to understand, and techniques, usually, for example, hard X-rays will overlap and continue to low energy gamma rays. And if you look at the frequencies, it is greater than about 3 into 10 to the power of 19 hertz. So, and you can see that over here as well, that this is 10 to the power of 19 hertz. So we are looking really at the high energy part of it. And then if you look at energies, it is greater than about 120 or so kilo electron volts, right? So this is in electron volts, so 10 cubes, so 100, it'll be about 120 or so. And if you want to compare this with a radio photon, for example, as we did in the case of X-rays, you can find that these are at least about 10 to the power of 9 orders of magnitude higher in energy. Here I've taken a lambda equal to 1 centimeter wavelength of a radio photon, which corresponds to about 3 into 10 to the power of 10 hertz, okay? And that gives you about 1.2 10 to the power of minus 4 electron volts. You can verify these numbers for yourself as well later. And if I look at an optical infrared photon at about 10 to the power of minus 4 centimeters, which is about 10,000 angstroms, getting into the infrared region of the spectrum, beyond the red end of the spectrum, the energy is typically about 1.2 electron volts. So even with respect to the optical photons or optical infrared photons, you can see that this is about 100,000 times more energetic than the optical infrared photons that we are talking about. So gamma rays are indeed the most energetic component of the electromagnetic spectrum. So where would you, given this background and given what we have discussed so far, so where would you expect, or from what kinds of sources, and also from your knowledge of basic physics, what kinds of sources would you expect to be emitting in gamma rays? So let's discuss that briefly. Any one of you can unmute and say.
Because they're so high energy, I'd expect them, perhaps the collision of two like fast moving particles if they were moving quite fast. Or I think they're so high energy, they would be released in supernova as well, right?
Okay, okay, no, that's one aspect of it. Thank you very much. So anybody else? That's correct, actually. And any other aspect that any one of you would like to highlight? From your basic physics that you have done, as we just mentioned, that radioactivity, isn't it? Radioactivity emits alpha particles, beta particles, so electrons, and gamma rays. So in astrophysical situations too, when you synthesize elements which are radioactive, they could undergo nuclear decay processes, and you could get gamma ray emission from that. We will look at in a bit more detail about the different processes qualitatively, because at this level of the course, we will not get into detailed mathematics. But as you can see, one is, of course, high energy particles in strong electromagnetic fields, and then nuclear decay processes and nuclear interactions. So basically, nuclear and high energy universe is what determines the gamma ray photons that we see. And looking a little bit back in the history, that discovery of the pi meson in 1947, and noting that the pi 0 can decay into two photons, that one realized that gamma rays could be produced by charged cosmic rays. Cosmic rays, although it is called rays, these are actually particles, high energy particles. And so the ancestors or the forebearers of gamma ray astronomy were cosmic rays or cosmic particles, and nuclear physics and elementary particle physics as well. And as Aquino mentioned, that supernovae and supernova remnants, because they are highly energetic phenomena, are natural sources to expect gamma ray emission from. They're also, because radioactivity also plays an important role, the sites of nucleosynthesis, for example, where you could get gamma ray emission from. And also, suppose there is both matter and antimatter. Suppose there are positrons and electrons in a certain region of space. Then again, you could get electron-positron annihilation and emission in the gamma ray region of the spectrum. Okay, so these are all high energy phenomena, but just to give you a glimpse, and we will recap and revise as we go along. Actually, interest in gamma ray astronomy really sort of picked up quite a bit after a very interesting paper by Philip Morrison in 1958 in Novo Cemento, titled On Gamma Ray Astronomy. And he looked at the kinds of sources, celestial sources that might be emitting gamma ray emission. Although the estimates he made were very optimistic, and gamma ray astronomy really took some time to take off. And in the meantime, X-ray astronomy developed by leaps and bounds. But gamma ray astronomy too has come of age. And today we have very detailed observations of the gamma ray sky. Just as the radio window is large, you can see that the gamma ray window is also extremely large. For example, if you look at about 100 keV, which is about 10 to the power of 5 electron volts, it goes to about 10 to the power of 20 electron volts or so, about 100 extra electron volts. So you can see this is about 16 decades in energy, or about 16 decades in frequency. Although most of the studies are confined to about 100 keV to about 100 TeV, but the gamma ray window is extremely large. So you can ask yourself the question that how high can the frequency be? Okay, and how energetic a photon can the universe produce? Okay, and clearly there has to be a limit; it cannot be infinity. But what are the highest energy photons that one detects, or one is detected, or can be produced? I will leave it to you to sort of investigate that. But and we can probably discuss it later in class, in another class. So these are also sort of divided because different processes play an important role in different energy ranges into low and medium energy, so which is about 100 keV to 30 MeV, high energy from 30 MeV to 100 GeV, and very high energy from 100 GeV to about 100 GeV. These are the normal ranges which one normally uses. So we'll first have a look at the gamma ray sky, and then we will look at some of the instruments or telescopes that have gone up. But while doing that, I'd just like to highlight a couple of things. One is that in radio as well as infrared, optical, ultraviolet, and we shall see to some extent in X-rays, what we are trying to do is concentrate a photon beam. Okay, in the radio telescope case, you have a parabolic dish or a cylinder which focuses the incoming radio waves into the feed, or which lies at the focal point of the parabolic cylinder. And you also saw that how infrared, optical, and ultraviolet gets focused by mirrors. Initially, it was by lenses, but now it is more by mirrors. And X-ray telescopes will come to as well in a short while. And in all these cases, generally the detector is a small fraction of the aperture. You collect light over a large area or radiation over a large area, and then focus it onto your detector, which is a small fraction of the aperture, which is either a mirror or an antenna. But when you come to the highest energies, above a few MeV, there is no effective way of focusing the photon beam. So you have to detect it directly. So detectors are effectively the size of a gamma ray telescope. So they're usually small in size. That does not help. I mean, as we saw earlier, that gamma rays don't come through the atmosphere, they don't penetrate through. So you have to put telescopes in space, and it is very difficult to put huge dishes in space. And particularly the photon flux is small. I've just given you one example over here, which is at 100 MeV, mega electron volts. The Vela pulsar, which was one of the very early gamma ray sources which was known, has only 1 photon per minute. Okay. So if you want to detect a reasonable number of photons, then you have to have a much larger, a reasonably large aperture, or you have to integrate over a long period of time. And these challenges have been overcome. And today we have a view of the sky, which we'll see in a short while. But as you go higher in energy, the number of photons decreases even further. So at a very high energy, it is almost impossible to go and outside the atmosphere and put telescopes and detect gamma rays from outside our atmosphere. So at very high energies, above 100 GeV or so, we have ground-based telescopes. Now, how do ground-based telescopes work when the gamma ray photons cannot come through? Is something which we will discuss a bit more later. But basically, we use the whole atmosphere as a telescope here. Normally, we have always discussed so far as the atmosphere being a bit of a nuisance, giving rise to blurred images, cutting off light. But here, the high energy photons interact with particles in the atmosphere to generate an air shower. And it is this air shower, as well as particles traveling faster than charged particles traveling faster than light in the medium, gives rise to what is called Cherenkov radiation. We try to detect that pulse of Cherenkov radiation. And those are the kind of techniques we'll discuss a wee bit more, not getting into any great detail, but just bear in mind that different processes are used to detect gamma ray photons in different energy ranges. And at the very high energies, these are based on ground-based telescopes, which depend on interaction of the gamma ray photons. Yeah.
Isn't Cherenkov radiation caused by particles moving faster than the speed of light in a particular medium? So what precisely causes the Cherenkov radiation in the atmosphere if it's not the gamma rays themselves?
Because gamma rays will give rise to secondary particles, and the secondary particles will travel at velocities which are greater than the velocity of light in the medium. As we see, when gamma rays interact with the medium, they can knock off electrons, they can accelerate electrons, they can create pairs of particle and antiparticle, like the electron and positron. Okay, so it is these secondary particles, charged particles, which are traveling with velocities greater than the velocity of light in the medium that will give rise to Cherenkov radiation. Now let's have a look at some of the main sort of contributors to the gamma ray sky. Now, some of the very early telescopes which went out were in 62 and 68, Explorer 2 and OSO 3, and they laid the groundwork for the growth of gamma ray astronomy. But the important sort of missions which really made a dent were the small astronomy satellite 2, which was a NASA mission which went up in 1972, and COSB, which was an ESA mission which went up in 1975. And what they noticed was a diffuse background, which you can see in this image as well, from the galactic plane, from the plane of our galaxy. But there were two of the very prominent sources which stood up, was the Crab pulsar and the Vela pulsar. Okay? And the Crab and the Vela pulsar, you can see it in this. This is a much later image from Fermi, and this gives you the locations of the pulsars which Fermi have detected. This is perhaps not the most recent picture, but this is Vela pulsar over here, and this is the Crab pulsar over here, close to the galactic plane. Okay, and these are pulsars which are the result of supernova remnants, and these pulsars generate very high energy particles which are accelerated along the field lines. And we see it as pulsars, for example, when the radio beam, which we talked about earlier, about when we discussed Jocelyn Bell's discovery of pulsars, that the star is a neutron star, which is a remnant of the explosion of a massive star greater than several solar masses. And it has a very strong magnetic field of the order of 10 to the power of 12 Gauss or so, some significantly higher than that, and spinning very rapidly with time scales, periods of about millisecond or so. And in these rapidly rotating objects with very strong magnetic fields, particles are accelerated along the field lines, and these particles give rise to the pulsed emission that you see when that cone of emission cuts your observatory or the telescope with which you're observing. If the beam is pointed away from you, then you will not see the pulsar. It may be a pulsar, but you will not see the pulsar if the beam doesn't intersect your observations, your telescope you're observing with. So Crab and Vela are two of the very energetic pulsars, and these were discovered very early on by the mission, COSB mission, which went up in 75. Actually, SAS2 unfortunately did not last very long, but COSB lasted many years and made some very important and fundamental contributions. So in the 70s itself, there were the pulsars were detected in the gamma ray region of the electromagnetic spectrum. So you knew that particles were being generated in pulsars which radiate at very high energies. They also found an object over here, which is marked over here, called Geminga. Geminga is a very unusual object, and that is illustrated by the slide which I picked up from a presentation by Lynn Kominsky of Sonoma University. And what you see over here is that this is the Crab pulsar, and you can see it across the electromagnetic spectrum. And all the pulsars except Geminga, which have been detected at gamma ray wavelengths, also have radio pulses. Okay. Now, except Geminga. So Geminga was, I think, the first probably radio-quiet isolated neutron star where pulsations were discovered at X-ray, at gamma ray energies, and also at X-ray energies, as you can see, but not in the radio region of the spectrum. Today, there are many more examples of this sort, and these have actually remained quite interesting to study and find out why that is the case. It is possible that the beam of radio emission in this case is not pointing towards you. The locations of the pulse emission from which you see at high energies may be different from that which you pick up normally in radio pulsars at lower energies than X-rays and gamma rays. But these are extremely exotic classes of objects.
Are the gamma rays emitted from the poles of the pulsar?
It could be from the magnetosphere itself, so it is probably from the magnetosphere. Okay, but particles will have to get accelerated starting from the poles, but the emission could be from the magnetosphere as well. So here is a galactic distribution in the galactic coordinates of pulsars which have been detected by Fermi at gamma ray energies. So besides Vela and Crab, you can see that there is the diffuse gamma ray emission in the plane of the galaxy, which is possibly due to the high energy particles generated, as you all said, in supernovae and supernova remnants, which are diffusing in the plane of the galaxy, confined largely to the plane of the galaxy. And a lot of the pulsars you see are in the plane of the galaxy itself. But there are also several which are not in the plane of the galaxy, but at high galactic coordinates. Many of these are actually millisecond pulsars. So you remember that population 2 objects we talked about were more spherically distributed, but the pulsar generally, most of them are in the plane of the galaxy, but there are also pulsars which are associated, for example, in globular clusters. You estimated very early on about the density of stars or the volume occupied by stars in our galaxy, and you came into an absolutely minuscule number. But when you talk about globular clusters are densely packed stars. They could consist of thousands of stars in a small volume of space. So there could be much more frequent interactions. There could be companions which could be captured, and pulsars could be spin up by material accreting onto the pulsed object, onto the neutron star. And it is interesting that if you take that further, that the millisecond pulsars which have actually a more uniform distribution than being entirely confined to the plane of the galaxy. In fact, one of the very well-known globular clusters is 47 Tuc, in which many millisecond pulsars have been discovered at radio frequencies. And this was one of the objects, which was one of the globular clusters, which was studied in great detail in the very early days. And pulse emission from the pulsars in 47 Tuc have also been detected at X-ray and gamma ray wavelengths. This lower figure actually shows you the development or the number of pulsars that are known. Okay, I took it from a review by Carivio in 2014. This figure is also from there, and this 150 comes from that review. But I think the numbers have grown since then. And these are the telescopes which I mentioned about. SAS-2, which did not, it's a small astronomy satellite. It's a NASA mission, which went up in 72, I think. And COSB over here. And then the more recent ones, EGRET Agile, which is an Italian mission. And this is a collaboration between a few nations, including the United States and Italy. And what you see over here is what is marked over here in numbers, okay, is a number of photons, the maximum number of photons in the highest bin that they have detected. And you can see because of the increased sensitivity of the detectors, you can see that the energy resolution is also much, much better. Here, there were a much fewer number of bins compared to what you're able to do with Agile or Fermi. And because of the sensitivity of Fermi, in the highest bin today, you have 25,000 photons coming in, whereas in the case of SAS-2, it was only 25. So there has been a 1,000-fold increase in sensitivity of photons from the Vela pulsar. These profiles which you have shown are for the Vela pulsar, which I mentioned earlier was one of the very early gamma ray pulsars to be detected. What is shown in shaded blue over there is a number of detections. And you can see that what happens over here is that technology has actually played a major role, from the kind of detectors that were used to more recent solid-state detectors, which have really revolutionized sensitivity. So in astronomy, you'll often find that technology developments have played a major role in new discoveries and in the growth and development of a field. Now, one of you mentioned about supernova remnants, okay? And And here you can see some of the prominent supernova remnants detected by Fermi. This is IC 443. Let me see if names you remember. Cassiopeia A is a name you remember. Tycho's supernova remnant, which Tycho Brahe actually noted and saw. And there are others on the plane of the galaxy as well. Okay, W28, etc. Okay, now what you see over here is that the supernova remnants are largely confined to the plane of the galaxy, because these are the remnants of the explosion of massive stars, and these are generally short-lived. Massive stars live in timescales of millions of years, whereas stars like our sun or lower will live in timescales for billions of years. So in addition to the supernova remnants, which are sites of particle acceleration to high energies, which you all have correctly mentioned earlier, that even a supernovae which goes off can be a powerful source of gamma rays. And as we mentioned, that when a supernovae goes off, there are a lot of elements which get synthesized, and because of the dense high temperature and the conditions which exist, density which exist in those situations, and many of them could be radioactive. So radioactive decay giving rise to gamma ray lines can also give rise to emission at these high energies. Now, suppose we look at what are the kind of extragalactic objects which emit gamma rays. In the early missions, the object which was discovered at gamma ray wavelengths as well was the first quasar that we know of, 3C273, which was discovered, as I mentioned earlier, at radio wavelengths. But I'd also mentioned that these are copious emitters at high energies. And if X-ray astronomy had come up earlier, it would have been discovered in X-rays. And if gamma ray astronomy had come up earlier, it would have also been discovered in gamma rays. It was one of the very early sources to be discovered at gamma ray energies by COSP, besides the carbon Vela pulsars and the diffuse background and Geminga, which we discussed earlier. The extragalactic objects, they would have no special location relative to us, our location, our galaxy in any way, right? They will be, the universe is homogeneous and isotropic on large scales. So in some cases, for example, that was one of the ways to find out whether objects are galactic or extragalactic. In case of extragalactic objects too, there would be no preferred plane, no preferred location as far as our galaxy is concerned, because we don't reside in any special place in our galaxy. Our galaxy has no special place in the universe. We are just an ordinary galaxy, have an ordinary galaxy, a spiral galaxy, and we are a planetary system in a very ordinary star located about 8.5 kiloparsecs from the center of our galaxy. So if these sources are uniformly distributed in the sky, then it is likely to be extragalactic, even if you can't find optical counterparts for these objects. That is the way one of the early arguments suggests that a kind of active galactic nuclei called BL Lacertae objects, where there were no emission lines were detected or absorption lines detected in the early stages, that the distribution suggested that they were likely to be extragalactic. In the case of these gamma ray sources, we of course have measured redshifts for most of these objects, and some of the very well-known ones are marked over here. For example, the first quasar, 3C273, another quasar, 3C279. Then you have BL Lacertae here as well, which is a prototype BL Lacertae objects. And this is another very well-known quasar, 3C454.3. This is a well-known Seafood galaxy, Markarian 501. These were cataloged by a astrophysicist, Markarian. Then there is a very well-known blazar called 0716 plus 714, which you can see over here. So basically, these are objects which have very high energy photons. They generate gamma rays, and that is how you're able to observe them. So whenever you see objects uniformly distributed in the sky, they are likely to be extragalactic objects. Of course, population 2 object globular clusters, which you can easily identify, are also uniformly distributed in a spherical halo of our galaxy. But here you can see that, that these objects, these energetic objects, actually have jets of relativistic plasma, which are beamed towards us often. They generate very high energy particles by various processes, which we will recap again today, because we keep discussing this off and on, mentioning it, but we will recap and revise that again so that you're familiar with the names and physical process, although in an introductory course, we will not get into the detailed derivations of the formula. So you can see that from over here, that that there are very energetic events, both in our galaxy as well as external galaxies, which generate emission at gamma ray frequencies or wavelengths. And these classes of objects all belong to what are called active galactic nuclei. They are not ordinary run-of-the-mill galaxies like our galaxy, with not very strong nuclear activity, but these are absolutely, generally, usually, they have very luminous nuclei generating high energy photons, ultimately due to accretion of matter onto a supermassive black hole residing in the nucleus of the galaxy. And as I mentioned, they usually have jets of relativistic plasma going out at velocities very close to that of light and coming towards us. Now, as I said, we'll just recap a little bit on the physical processes which are responsible for the emission. This is just a recap. Now, one is bremsstrahlung, which we talked about in the case of optical emission as well, and also in the case of radio emission, also in the case of X-ray emission. So bremsstrahlung or free emission, they're called free because the initial electron is also free and the final electron is also free. But during the interaction with a proton, an ion, that they are accelerated. And as a result of that, they give out a photon. So it's high-speed collisions between electrons and ions or protons, because protons are far more common. High-temperature plasma will produce photons of higher energy. And if you have X-rays and gamma rays, they would have to be at least millions of degrees Kelvin. So when they are moving, when there's a high temperature plasma, they're also moving about at much higher velocities. And so to get free emission at these high energies, you need extremely high temperatures. The other process which we talked about is synchrotron radiation. Here is just an illustration of it. It was also called magnetobremsstrahlung in the earlier days, just as free emission was called bremsstrahlung or thermal bremsstrahlung. And this comes from the German word for breaking radiation. A lot of the early days, many of the seminal papers were published in German. And what you can see over here is that this is due to an ultra-relativistic electron moving in a magnetic field, which gives rise to these X-rays and gamma ray photons. We spoke about this in the context of radio frequency emission as well. Okay, and the difference is essentially is the energy of the particles that are emitting. So most of the energy, if you take a single electron in a given field, that most of the energy is emitted at a frequency which is proportional to the square of the Lorentz factor of the electron. Lorentz factor, as you know, is 1 divided by square root of 1 minus v squared by c squared. Okay, so as v approaches c, the Lorentz factor gets larger and larger. If v is equal to c, then obviously the Lorentz factor is infinity, but only light travels at the velocity of maximum velocity of light. Okay. So gamma squared be the perpendicular component of the magnetic. Now, suppose I had an electron, just to give you an idea and connecting it to what we did earlier, that if we had an electron with a Lorentz factor of 10 to the power of 4, okay? 10 to the power of 4 it means you can see how many 9s I've written over there. Moving in a magnetic field of 10 microgauss would have a maximum energy at only 1 gigahertz. Okay. Now you want radiation at 10 to the power of 19 hertz, at least, to be in the gamma ray region of the electromagnetic spectrum, right? So you need gamma squared to increase by about 10 to the power of how much? So you estimate that. I'll leave it to you as an exercise to do, but you can see that it is many, many orders of magnitude. And you can imagine that how many more 9s I've got to add over there. So you have electrons which are effectively moving at the velocity of light, just a tiny wee bit below the velocity of light, that these exotic and energetic phenomena have been able to accelerate particles to those high energies. And when you have that particle accelerated to those energies, then you will get gamma ray emission due to synchrotron emission. We also mentioned in the last class about the spectrum of the X-ray emission, which is a power law. That is also true of radio emission, as we saw earlier. And that is because there are many more electrons at lower energies. Okay? Because at lower energies means lower gamma. Lower gamma means the emission is peaked at a lower frequency. So you have many more electrons at lower frequencies. And if you add up all these emissions, this is what you will get. At higher energies, the number of electrons are far fewer. And these high energy electrons also emit at a higher frequency, which is proportional to the magnetic field and the square of the Lorentz factor of the electron. So we have a situation over here that the number of electrons energy distribution also goes down as a power. Okay, so there are many more electrons generating photons at lower frequencies compared to those at higher frequencies. Low energy photons, the peak of emission is at a lower energy. Higher energy photons, because of this expression, peak at a higher energy. So if you had an electron energy distribution, which is also a power law, with an index of P over here, then the flux density versus frequency, which is the usual observed spectrum which you see, would also be a power law, and the two indices would be related by this expression. So if you had alpha of 0.5, you can see that you would need P to be 2. 2 minus 1 is 1, 1 by 2 is half. For alpha to be 1, you need P to be 3. So 3 minus 1 is 2, by 2 is 1. So a power law distribution of the radiating particles will give you a power law spectrum. And as you can see, that the higher the energy, your photons you want to get, higher the energy of the electrons you require. And for gamma ray energies, you require the photons to be almost traveling at the velocity of light. Okay. Even at radio, you can see it is pretty close, very close to velocity of light. But when you come to gamma ray photons, you'll have to add many more 9s over here. Now, what are the other processes that we want to do? One is something called the inverse Compton emission. We'll keep coming these terms when we talk about astronomy and astrophysics. So I'm trying to introduce you to them in a very qualitative way. You'd have perhaps studied about Compton Effect in your undergraduate classes, where you have an electron which moving at low velocities, or electron in an atom or electron, where a photon gives energy to the electron. Let's say an electron at rest in an idealized situation. The electron will get energy and momentum from the photon, and then photon will lose energy. So you'll have a lower energy photon after the interaction. In that case, you have electrons which are not zipping about at high relativistic velocities. In these highly energetic objects, what we have seen is that, for example, to give rise to the synchrotron emission, which we talked about, you need electrons which are moving at effectively, nearly the speed of light, differing it only by, one in many, many, many parts. So what happens in that case is that a low energy photon can interact with these highly relativistic particles and be scattered to higher frequencies. Okay. So I've just written down the expression over here. A photon of frequency nu after scattering with a relativistic electron of energy gamma MEc squared, where Me is the rest mass of the electron and gamma is the Lorentz factor, 1 upon square root of 1 minus V squared by C squared. Okay. And that gives you an expression for the energy relativistic electron. And the upscattered photon will have an energy which is given by nu IC equal to gamma squared nu. If nu was the original frequency of the photon, after an inverse Compton scattering with a relativistic electron, the emitted photon will have a frequency nu IC. IC stands for inverse Compton over here, which is of the order of gamma squared times larger. Now, again, you can see over here, I've given, because we had discussed this earlier, I'm trying to again relate it to what we saw in the radio regime of the spectrum. In the radio region of the spectrum, if you had a 10 to the power of 4 electron, 10 to the power of 4 Lorentz factor over here, and you had a frequency of 1 gigahertz, which is 10 to the power of 9 hertz, then 10⁴ squared 10 to the power of 8 plus 9 would give you 10 to the power of 17 hertz. That would be in the X-ray region of the electromagnetic spectrum. Now, you can imagine the kind of Lorentz factors we talked about, which could be orders of magnitude higher than what we have discussed over here for the radio photons. Okay. Then you can easily see that these could be scattered into the gamma ray region of the spectrum. Also, if you had higher frequency photons, over here, I've considered 1 gigahertz, but it can go up to millimeter wavelengths, 100 gigahertz. Then again, you can see that, you can get even higher energies with a combination of both high frequency photons, which are being upscattered, and higher values of the Lorentz factor. So this is an important process in active galactic nuclei, and where jets are moving at relativistic velocities, and you can have highly energetic relativistic electrons over there in the vicinity of the black hole as well, where they could interact with lower energy photons, upscattering them to high frequency photons, hard X-rays, and gamma ray region of the electromagnetic spectrum. Two other processes which I've mentioned over here in terms of continuum emission is curvature radiation, where in the strong magnetic fields, strong fields which get generated in the pulsars, that the radiating particles could be constrained to move along the field lines. And when they're accelerated along the field lines, they can give rise to emission at gamma rays. Here I've given a number for a 10 to the power of 13 electron volt moving in a field with a radius of curvature of about 10 to the power of 8 centimeters would be 2.5 GeV. But basically it is, one should realize that in these strong fields, the electrons or high energy electrons can be accelerated along the field lines and give rise to emission at high energies. Then the process which I mentioned over here is electron-positron annihilation. So the rest mass energy of an electron is 511 keV. And when an electron and positron annihilate, you could get a line at 1.02 MeV. But again, the electrons and positrons have their own energies as well, because they're not at rest, they're moving about at high velocities as well. So what you get is when they annihilate, if there's an electron and positron population over there, you would get 2 gamma ray photons. But because if they're moving at highly relativistic velocities, then you'd also get a continuum of emission due to electron-positron annihilation. These are 2 more processes which I will just mention, but they play an important role as well. Here, these, for example, when proton interactions take place in the lower curve, it is shown over here, that I have not written down all the reactions over here, but when protons interact, they give rise to, some of the reactions give rise to pi mesons or pions, and the pi 0 decays on a very short time scale to 2 gamma ray photons. Similarly, you can have protons which interact with photons to again produce pions, which again decay very rapidly into gamma ray photons. So these are called hadronic processes because protons belong to this class of fundamental particles called hadrons. So these are some of the properties, some of the emission processes for continuum emission at gamma ray wavelengths. And as you can see, and as you all correctly pointed out, it is all to do with very high energy phenomena. Now, when we talk about, we have so far talked about continuum emission, but there are also lines emission, as we mentioned earlier on. One is, of course, the positron-electron annihilation line, which is 2 gamma ray photons get emitted. Neutron capture can lead to photons at a particular wavelength, frequency, or energy. This is proton capture by hydrogen. You need high densities for that. If you excite nucleons by interactions with cosmic rays, then radioactivity, these can all give rise to emission lines at gamma ray frequencies. You don't have to remember each one of them, but this is just to give you an idea of the kind of different processes which give rise to emission lines at gamma ray wavelengths. We mentioned quite early on about radioactive decay, and titanium gets synthesized in supernova explosions, core collapse supernovae over here, supernovae nucleosynthesis. Then there is also positron annihilation, which we talked about, radioactive decay we have talked about, and then cosmic rays can excite nuclei to high energy states, and when they come down to lower energy states, they can again give rise to gamma ray emission lines. So you can see at the highest energies, you can get both continuum emission as well as line emission at gamma ray wavelengths. And one of the very nice sort of illustrations of gamma ray emission lines is to look at the light curves of a supernovae that goes off. Here is a V-band light curve of supernova 1987A. So initially, V magnitude is an optical magnitude in the V band, and we shall see later that the larger the value, the fainter an object is. Smaller the value of the magnitude, the brighter an object is. So you can see it peaks and then it decays. All right. Now, and what happens is that when the supernova goes off, that it leaves many nuclei in excited and unstable states. Now these decay, giving rise to gamma ray photons, and the gamma ray photons interact with the medium, and then ultimately you see the emission coming out, which you detect at different wavelengths. And the light curve of this can be very nicely interpreted in terms of the radioactive decay of elements. And the radioactive decay, for example, when 56 cobalt goes to 56 iron, from Z equal to 27 to Z equal to 26, it has a 77-day period, half-life. Okay? So you can actually understand the light curves of these supernovae by invoking radioactive decay of the elements which get synthesized during this violent process. Now, ones which have short lifetimes, you will see it in the early phases, and the ones which have long lifetimes, you will see it in the later phases. Okay? And you can try, and this has been very nicely modeled in terms of, I mean, there are other aspects as well, for example, dust formation, how does it affect it? But the radioactive decay of the elements which get synthesized is very nicely seen over here. Now, one of the elements which gets synthesized is 26 aluminium. Okay? And that has a very long lifetime. Unlike cobalt 60, which I mentioned, which we just saw a little while earlier of 77 days, that this is about 730,000 days or so. So that means when you see aluminum 16 line, okay, that means that you are trying to see activity which is integrated over a long lifetime. Unlike a supernova which goes off and decays in months or years, but these would be in, you can see it's nearly 1 million years or so. And the lifetimes of the massive stars, which you'll see later in more detail, which explode as supernovae, are on a similar time scale. Okay. So when you look at aluminum 26 line from the galaxy, this is an image of it. Okay. And you can see this is the aluminum 26 line. The 26 aluminum, which has a line at 1.809 MeV, they trace regions of recent star formation because their half-life is similar to the lifetimes of massive stars. They integrated over this star formation activity. And it is not just from supernovae, but also there are very massive stars called ultra-ray stars from where you might see this element. But basically, it forms a very good tracer of recent star formation activity. Just as we talked about H-alpha, which we trace star formation because regions of hydrogen gets ionized by the hot young stars. But here we have another indicator of star formation in the gamma rays part of the spectrum. So you can see that both continuum and gamma ray emission play an important role in our understanding of the universe. This first part, I will draw your attention to another object, classes of objects, and then we will stop. These are the gamma ray bursts. They were discovered serendipitously by the VIII satellites. The VIII satellites were put up by the US to monitor possible nuclear explosions in the 60s. And nuclear explosions gives rise to a burst of gamma ray emission. And they were there to monitor whether the Russians were upholding the treaty or not, or whether they're doing things sneakily. But what they found were bursts of emission, which could not be ascribed to explosions which the Russians may have carried out. Later observations followed and led to the discovery of these bursts of emission, which are seen in the gamma ray or the high energy part of the electromagnetic spectrum. Later, they were also found in X-rays, and after this burst, there's often an afterglow, which is studied across the electromagnetic spectrum. And these explosions could release 300 times as much energy in a few seconds as our sun does in its entire lifetime of 10,000 million years. And they are the most powerful explosions in the universe. And to understand their energetics, actually, you need some of the emission to be beamed or enhanced towards you. This little GIF file over here, which I've taken from on the NASA side, shows you this gamma ray burst going on. It's literally time in seconds. And you can see that when at its peak, it's gone off, it literally overwhelms the gamma ray sky. But it lasts for a very little time. So short duration bursts and long duration bursts, they seem to be two categories. Short duration bursts are typically less than about 2 seconds, and a long duration burst longer than that. Short duration bursts are believed to be generated due to colliding neutron stars or neutron star black hole collisions, whereas long duration GRBs, they're related to hypernovae, which is very powerful supernovae from very massive stars, greater than about 20 solar masses or so. And if you look at, again, these are from external galaxies. So just as we saw that AGN were emitting in the gamma rays were uniformly distributed, they are uniformly distributed in galactic coordinates. Plus 90 and minus 90 refer to the North Galactic Pole and the South Galactic Pole. And galactic equator is seen with the longitudes from plus 180 to minus 180 shown. And how do we know that how energetic they are? We had to find optical counterparts of it, measure the redshift and measure the distance. And this required quite a lot of ingenuity because as you saw, they go up very rapidly and then decay. And you need to catch them when they're bright at the optical wavelengths as well to be able to measure a redshift. So there was a framework or setup for rapidly following anything, any gamma ray burst that goes off, and telescopes would be immediately alerted across the world, and within seconds, literally, they would try and go and follow this object. So this particular set of figures which I've taken is from the Robotic Optical Transient Search Experiment called ROTC-1, which is located in Los Alamos in New Mexico. And this particular one was picked up just 22 seconds after Compton. So I think it was middle of the night, but these are all robotic telescopes. The moment they're alerted, they go and follow this object. It measured a redshift of 1.6 at about 39.2 gigalight years away. So this is a distribution of the luminosity of these objects. Okay. So this is at a redshift of 8.2. You can see that these are from the furthest reaches of the universe. Okay. And you can see the energies over here, the highest values that it goes to. So if you take 10 to the power of 33 or a few times 10 to the power of 33 ergs per second as a solar luminosity, the energy that it will generate in a year, you have to multiply it by the number of seconds in a year, which is roughly 3 into 10 to the power of 7. So you'll get 10 to the power of 41. Okay, 10 to the power of 33 plus 7, 10 to the power of 40, another 41 over here. So you put in 10 billion years, 10 to the power of 9, 10 to the power of 10 billion years. So you can see that these energies at the higher end are larger than what the sun would emit in its entire lifetime. Energy generated and emitted in just a few seconds. So you can see the opening up of the highest window has also led to a very rich universe, which we would not have been aware of if we were confined to lower energies, whether it be optical, infrared, or radio. Each new window that has opened up has brought its own share of surprises.